All right, good morning. So I finally figured out what I was doing wrong with the lockdown browser issue. So exam one is finally up because of the late post. It's going to be due tomorrow night at midnight. Um, you'll see just to make sure that everyone's on the same page. Again, let's go back and do a quick share. And if you go to the Canvas site for the class, you'll see below the class video link, you'll see an exam module. And there are three things you're going to have to use. Dagnabbit. You'll want to go here to set up your lockdown browser. If you haven't already installed it, it will prompt you to install it there. But then you're going to have to open a quiz using lockdown browser. And one of the things that one of my students ran into the other day was she went through the process of installing stuff, but then she kept going back into this assignment from her regular browser, and it kept prompting her to download and install it again. And don't do that. Use the lockdown browser, go to Canvas, open any of these items here using that browser, and you should find that it will be able to unlock for you and you'll be able to take the exam. So make sure you do this first one just to make sure all the technical kinks are worked out as soon as you can. Because if you run into a problem, if you wait until 11 o'clock on Wednesday night to discover that you have a problem, it's too late for me at that point to do anything about it. So try to troubleshoot issues. Again, this lockdown browser will work on any sort of laptop computer, a Mac or a Windows-based computer just fine. You can also run lockdown browser on an iPad if that's a preferable device for you. If you're going to do that, make sure that you can set your iPad up to position it so that it can get a clear view of your working space while you're doing your work. But that's an option. If you have any technical glitches, please let me know as soon as possible. We'll try to figure them out. But that's something you should be doing in the not so distant future. In the meantime, let's press forward and learn more physics. We've been talking about circular motion for the last couple of days. And the key insight when it comes to circular motion is that motion in a circle means you're accelerating because your velocity has to constantly be changing direction. And we figured out how much that change was. And we delineated that as A sub C, where A sub C is equal to V squared over R. And this was called your centripetal acceleration. So anytime you see an object moving in a circle, you know that the acceleration of the object has to be equal to V squared over R towards the center of that circle. And we did some examples yesterday where we had Spider-Man spinning around in a flat circle. We did an example yesterday where we dealt with orbital motion and with roller coasters. And all of those were objects that were fully traveling in circles. But here's the cool part. Just because an object is experiencing centripetal acceleration doesn't mean that it has to go in a full circle. Even an object that's only turning in a portion of a circle still can be analyzed using the same sort of technique. So here's an example I like to do, mainly because it gives me an opportunity to gripe about my little sister. So, true story. When I was in high school, I think it was my junior year, not sure it was my senior year. My little sister, who was at the time 15 years old and something of a juvenile delinquent, waited for me to be out of town for a week on a school trip. She skipped school with a friend of hers, stole my mom's spare key to my car that was sitting idle in the driveway. And even though she had never driven a car in her life and did not yet have even a learner's permit, she and her friend decided they were going to drive to McDonald's in my car. And that involved them going on the freeway and taking an exit ramp that kind of curved around. And when she did, here's what happened. So here's the exit ramp that kind of curved around. And what happened was she took that exit ramp at about 35 miles an hour. And rather than navigating through the exit ramp as she intended, what she in fact did was lose control of the car, skid into a guardrail, and did about $3,000 worth of damage to my car. So, yeah, that sucked. So the big question is, why did this happen? Why did she lose control of the car as she traveled through that turn? Well, we can analyze this question by thinking about the physics of Newton's laws and knowing what we know about centripetal acceleration. Because even though this little exit ramp wasn't a circle, it's only like a little 90-degree bend, we can imagine that this little 90-degree bend is a portion of a hypothetical larger circle. So the idea is that if I take this little radius here and I imagine extending it until it forms just one arc on a hypothetical circle, then I can characterize this curve with something that we call a radius of curvature. In other words, if this curve were a part of a circle, the radius of that circle would have been some number. So we would call that the radius of curvature of that exit ramp. And what was happening was my sister was attempting to enter this little purple section of that curve and hold that line. But in order to do that, she would have had to have sufficient force, in this case, acting as a centripetal force, to cause the velocity of the car to change from its original straightforward velocity and into that curved path. So if I want to break this problem down, the easiest way to think about it is to think about what the forces are acting on that car at that moment. So let's do a free body diagram for the car at the moment just prior to the crash. So to do that, let's think about it this way. Now, right now, we're kind of looking at a bird's eye view of the accident. We're looking down from the sky at the car as it travels. And so if I was doing a free body diagram, what's going to happen is I've got the force of gravity, which would be pulling straight down into the ground from above. That's kind of an annoying way to draw this. So I'm going to reimagine my perspective and imagine looking at this car from the back as she drives away from me. So here's the car. And imagine she's driving away from you. This is like her tail lights heading away. In that case, the force of gravity would point straight down into the ground. And that's going to be given by the force of gravity, mg. Now, the car is sitting on the ground, and the ground is pushing upward. We call that the normal force. Now, neither of those forces are what's causing the car to turn. So neither of those forces are providing what we call a centripetal force. What force would be causing a centripetal force? What's the force responsible for making that car turn? Any ideas?
The total force, the net force.
But that's the net force will end up making the car turn, but that's going to be a combination of several forces. So I need to drill down and know like what individual forces are acting on the object. So I've got the force of gravity, I've got the ground pushing up. What other things are going to be acting on that car that could cause it to turn? Well, to understand,
we have friction, right? Friction force.
Yeah, that's exactly right. Friction between the tires and the ground is the only other force we have acting right now, and it's the thing that's going to be causing the car to turn. And that frictional force is going to have to be acting as a centripetal force. It's going to have to point towards the center of the circle. So if I'm looking at the back of the car, the center of the circle will be to my right. So the frictional force would be like this. If I'm looking at the sky view version, the frictional force would be like this. And one thing that I often have students get kind of confused by is they're like, well, wait a second. The car is going this way. Why is friction not the other way? Why is friction not trying to slow down the car? And the answer has to do with what's happening to your wheels. Because it turns out that your wheels are rolling as you go. And that means that at the point of contact, the traditional sort of sliding kind of friction isn't really occurring. It's rolling without slipping. So as long as I'm not speeding up or slowing down, there's no net friction in that direction. So I don't need to worry about friction in this direction. But think about what happens to your car when you turn the steering wheel, right? What happens is your wheels are normally lined up with the velocity of your car so that they're able to roll very easily. But when you turn the steering wheel, what happens is your wheel pivots. Now it's able to spin in one direction, but the car's trying to move the other direction, which means the wheel is going to have to try to drag across the ground. And that's the frictional force that's causing you to turn. It's because your wheel wants to rotate one way, but you're trying to drag it perpendicular to the axis of rotation. And as a consequence, you get a frictional force that's pointing towards the center until the car reorients. And at that point, the wheels are rotating in the same direction your car is traveling again. So there are my three forces. And once we've identified my three forces, Newton's laws apply here just as they would anywhere else. So with this free body diagram, I'm going to break those three forces down into their X and Y components. And because this is a circular motion problem of sorts, I'm going to make sure that at least one of my coordinate axes points towards the center of the circle. In this case, this direction, or say that direction. So here is my X direction. Let's have positive be to the right. Here's my Y direction. Let's have positive be upward. And what's going to happen is when I break down my forces, it's going to be super easy. Nothing here is diagonal. So what's going to happen is for the friction, the J hat component is going to be 0, and it's all going to be in the X direction. So I could break it down, if I felt so inclined, as being mu times n. Remember, that's the force of friction, is the coefficient of friction times the normal force in the I hat direction plus 0 in the J hat direction. Same reasoning in the case of the normal force. It points straight up, but not sideways. So it'd be 0 in the X direction. And whatever the normal force is, all of it is in the J hat direction. And of course, for the weight of the car, it's not in the X direction either, but it's in the negative Y direction. So hopefully at this point, you guys are getting pretty good at being able to pick that out. There's no sines or cosines because there's no funny angles here. Everything's nice and happy and either horizontal or vertical and nothing in between. And that's going to make our lives way, way easier. So now when I go and do the third step, which is use Newton's second law, or F equals ma, to generate some equations, I'm going to get two equations, one for X and one for Y. In the X direction, I only have one force, and that's the friction. So this plus this plus this is mu times n, and that's going to equal the mass of the car times whatever that car's acceleration is in the X direction. That's one equation. In the Y direction, I have two forces. I've got the normal force upward and gravity downward. So the net force in the Y direction is going to be N minus mg. And that's going to be the mass times the acceleration in the Y direction. So once we've broken that down, we always pause at this moment and ask ourselves, do I know anything at all about the acceleration of this car at that moment in time? And the answer is I know plenty about the acceleration of the car. One thing I know for sure is that my car does not fly, no matter what my sister tries to do with it. So it's not going to move up and down. at all. That means there cannot be any acceleration in the y direction. So AY has got to be 0. Now, what about AX? Well, the x direction, remember, points towards the center of this circle that she's trying to drive the car around in. And that means that if I'm moving in a circle, my acceleration towards the center of that circle has to be equal to v squared over r. So what I can do is replace ax with v squared over r. So this equation is going to become, I'm going to write it over here, mu times n equals m v squared over r. So the force of friction is creating a centripetal force to cause this circular motion. Now, if I'm trying to solve this problem, I need to know some stuff. And one of the things that I know is that if you're looking at the frictional force between, say, a set of tires and the asphalt, the coefficient of static friction, mu s, between asphalt and rubber tires is somewhere in the neighborhood of about 0.8, right? Now, as long as my tires aren't skidding around that corner and I'm rolling normally without sliding, that's the coefficient of friction that I would expect to get. Once I start to skid, that number is going to go down, right? But as long as I'm not skidding, that's perfectly cool. So I have a number from you. That's pretty cool. N, I don't know. The mass of my car, I could look it up. I mean, she was driving a 1986 Mercury Cougar. But I'd have to look that up. V is however fast she's trying to drive, and R is the radius of curvature of that ramp, which, again, I could look that up. I still got to get rid of N somehow. And conveniently, N appears in 2 of my equations. I haven't used the second one yet. And when I solve that second one, well, you'll notice, oh, look, N is going to equal mg, which we can kind of file that under no duh. It says that the ground's going to push up just as hard as gravity pulls down. And that's why the car doesn't sink into the ground or fly up into the ground. Those 2 forces exactly cancel. But if I take N equals to mg and I plug that back in over here and replace N with it, I've got mu times mg equals mv squared over r. And you'll notice the mass of the car, which I don't know off the top of my head, doesn't matter. It's going to cancel anyway. So it wouldn't matter whether she stole my car or whether she stole my mom's car. The result would have been the same. So if you look, for a given radius of curvature, for a given tightness of that curve, you could solve for the velocity that you could take that curve with. If I just solve for v, I'll multiply both sides by r. I'll have mu times r times g equals v squared, and therefore the square root of r, mu times r times g, is equal to your velocity. So what we've just found here is that if we know what mu is, and we know what the radius of curvature is, we're going to figure out what the speed is that you can take that curve and make it through appropriately. So what happened to my little sister? Well, she goes into that curve, and she is not traveling this speed. She is instead going faster than that speed. Now, what's going to happen is friction can only turn you so much. The size of the force of friction can only get so big. And what that means is that if you make the velocity get bigger on this side, the only way this equation can stay true is if the r on the other side gets bigger, because mu can't get bigger. We can't make the ground grippier than it used to be. G is not going to get bigger because gravity is not going to suddenly get stronger than it used to be. So what happens is she goes through that curve traveling too fast, and she travels in a circle, but it's not the circle she intended to travel in. Instead, she travels in a larger radius circle. And unfortunately, that larger radius circle has her traveling through the wall. And hilarity ensues. So if you've ever experienced this sort of thing, if you've gone around a curve perhaps a little bit too sharply, you'll notice it seems to you, it feels like there's something pulling you towards that outside part of the curve. In reality, it's not anything pulling you towards the outside of the curve. In reality, what's happening is your car wants to keep traveling in a straight line. That's what the first law of motion says. And friction is causing that straight line to bend into some radius of curvature. But the faster you're going, the more friction you'd have to hold that curve. And at some point, you've exceeded how much friction you can use, and you can only bend it so much. And the curve you're going to end up going in is a little bit wider than the one you were trying to go in, and you hit the wall. So that's what explains that tendency of objects to hit the outside wall when they take a curve too fast. Now, if you've ever gotten off the freeway and you looked at those little yellow signs that give you the speed limits on those exit ramps, you know, where did they get the numbers for those exit ramp signs? This stuff right here, right? They figure out, they know how big the curve is because they built the ramp, and they can determine what velocity you can make it through safely. So we can apply this same sort of circular motion logic even to situations in which the object won't travel in a complete circle, but instead just travels in some portion of an incomplete circle. Super easy. We can knock ourselves out with that. But wait a second. Let's make it more complicated. Now, if you guys have ever like looked at a racetrack, like where they race professional cars, you'll notice that the roads there are not flat when it comes to those turns. The roads are kind of angled at a bank. And in fact, a few years back, my mother-in-law came to visit us, and we were looking for things to do in Charlotte. And even though I'm not really a NASCAR person, that's not really a thing that appeals to me, we took her to the NASCAR Hall of Fame. I mean, it's here in Charlotte, might as well, whatever. And if you go to the NASCAR Hall of Fame, kind of the main lobby area when you first go in, what they've got set up is this big sort of fake racetrack running around a big round room. And they've got all these, you know, classic cars from different points in history, you know, along that road kind of being displayed. But the road is inclined very much like the turns on one of the tracks. And in fact, at two different points, you're able to get up and kind of stand on it to just see how slanted they are. And like at one point, it slanted at, I think it was 23 degrees, which is the amount of banking that they have at the Charlotte Motor Speedway. But then further up around the corner, it's banked even more steeply at like 33 degrees, which is apparently the level of banking at like Daytona or something. So the roads are banked for some kind of reason. And to understand why they do that, why the turns on a racetrack aren't flat like they were here, but instead are slanted, we can figure that out too by thinking about the nature of the forces. So let's revisit this same sort of problem of a car going around a turn. But this time, rather than having the ground be flat, let's have the ground be slanted so that the inside of the track is lower than the outside of the track. How does that change our mechanics? Well, so here we are, we're kind of doing a back end view. So here's the back of the car traveling away from us. But now the ground is slanted at some kind of angle. And what's going to happen is we're going around in a circle. And again, we're looking at the back end view. The center of the circle is to our right. And the velocity of the car would be like into the page going away from our face. So if I'm going to break this problem down and I think about the forces acting on my car in this situation, well, gravity does not care that I'm on a slanty road. Gravity is still going to point straight down. However, the normal force from the road, because the road is now slanty, is going to itself be a little bit slanty. So my normal force is going to point not straight up, but off at some angle. Now, what about the friction? Well, the friction is was before pointing straight towards the center of the circle. Now what's going to happen is the friction has to be parallel to the plane of the road, and I'm going to have a natural tendency to slide towards the outside, so the friction is going to end up being a little bit towards the center, but now it's kind of diagonally and sort of annoyingly at the center. So those are my three forces acting on the car. And just like before, I'm going to take that free body diagram. I'm going to break my forces down into components, but it's going to end up looking a little different this time because the direction of those forces are no longer aligned the same way they used to be. Now, you might look at this and think, golly, that looks like a box on a slant kind of problem. So you might have an inclination to choose a slanty coordinate system for this problem, but that won't really help us much. Instead, we're going to want to choose a more traditional problem or coordinate system for this problem, because remember, we're dealing with circular motion, right? What this car is doing is it's going around in a circle, and I know that the acceleration towards the center of that circle is going to equal v squared over r, and I want to exploit that fact. But in order for me to do that, I'm going to have to make sure that either the x or the y direction points towards the center of the circle. Otherwise, I can't use this because my axes won't line up with it. So rather than choose a slanty coordinate system, I'm going to have my x direction point towards the center of the circle. That way I know the acceleration in that direction. And in the y direction, it's got to be perpendicular to that, so that'll be straight up and down. So when I go to break my forces into components, gravity is still easy. All right, the force of gravity is still going to be 0 for I hat minus mg for j hat. That was pretty straightforward. But when I do the normal force and when I do the friction, it's going to be complicated. So for the normal force, it's going to be a little bit straight up. So it's going to have a positive y component. It's going to be a little bit to the right. So it's going to have a positive x component. And I'm going to have to use sines and cosines to break it into pieces. And in order for me to do that, I need to know what angles I have. And one thing that I notice is that whatever angle my ramp makes, it's going to have to be the same as this angle right there. How do I know that? Well, if I imagine this angle dropping down to 0, my car would get flatter and flatter and flatter and flatter. But that means my normal force would point more and more and more and more straight up. And if this angle were equal to 0, that angle would also be 0. My normal force would point literally straight up. So that's how I know that this angle and this angle have to be the same. Now, if that's the case, the x component is going to be the opposite side of the triangle. And from SOHCAHTOA, that means I'll use the sine. So it'll be n times the sine of whatever the angle of my ramp is. For the y component, that's the adjacent side. That'll be the cosine. Notice the y portion is up, the x portion is to the right, so they're both positive. For friction, however, it's going to be a little trickier. Because for the friction, it's diagonal. It's going to have an x component, which is to the right, so positive, and a y component, which is down, and therefore negative. And again, from the same sort of logic, this angle here and that angle there are going to have to be the same. But notice for this triangle, the adjacent side is going to be the x component. So this will be mu sub n, that's the force of friction, times the cosine of theta, I hat, minus mu times n times the sine of theta for the j hat component, because the y component is opposite, that's why it's the sine, and it's pointing downward, that's why it's negative. So again, I've taken my forces and I've broken them down into their various components. And from that, I can then generate my equations. And in the x direction, I would get that by taking this plus this plus this. So I'll have n times the sine of theta minus mu times n times the cosine of theta. And that's going to have to equal the mass of the car times the acceleration of the car in the x direction. So that's one equation that I'm going to have. In the y direction, I'm going to have this plus this plus this. So notice this is positive, the other two are negative. I'm going to write that one first. So n cosine of theta minus the force of gravity minus mu times n times the sine of theta. And that's going to have to equal the mass times the acceleration in the y direction. So I've generated two equations using Newton's laws. And at this point, I always pause and I ask myself, for this specific problem, do I know anything at all about the acceleration of the object? And the answer is yeah, I do. One thing I know is that the car isn't going to be moving up and down at all. So in the y direction, the acceleration is going to have to be 0. In the x direction, however, that points toward the center of the circle. I'm moving in circular motion, which means a sub x I can replace with v squared over r. And so again, I have two equations and a bunch of unknowns, and I can solve for whatever it was I was going to try to solve. And what's particularly annoying is that you'll notice, the normal force appears a whole bunch of places. It's kind of an annoying thing to solve for. Theta appears a whole bunch of places. Kind of an annoying thing to solve for. However, conceptually, we can sort of see what's going on here. And we can see at least a little bit why the NASCAR people bank the curves like this. Because when we did this problem for the flat curve, we only had one force pointing even a little bit towards the center of the circle, and that was the force of friction. And the problem is the force of friction can only get so big before you start to skid, right? So there's a limit to how big that force of friction can get, and because there's a limit to how big that force of friction can get, there's going to be a limit to what velocity you can travel. That sucks. However, in this situation, what's going to happen is you've got two forces pointing a little bit towards the center of the circle, right? Sorry, that's a plus. So you've got the normal force pointing a little bit towards the center of the circle, and you've got the friction force pointing a little bit towards the center of the circle. So both of those forces are pointing a little bit towards the center of the circle. So both of these together are combining to be our centripetal force. And the thing about the friction is that you're limited as to how much friction you can get, but the normal force can be enormous. There is very little limit to how hard the ground can push on you, right? People can put really heavy objects like tanks and buildings on the ground and they don't fall through the ground. So the normal force can be huge, but because the normal force can be huge, that means that the velocity can be comparatively large as well. That means I can expect to drive around that curve faster than I otherwise would have been able to drive. And if we wanted to, we could totally solve for what that velocity would be. Now, I'll point out that a lot of times what happens is we will solve these sorts of banked curve problems for what we call the ideal banking angle. And the ideal banking angle is the angle at which you wouldn't even need friction. The normal force by itself could get you through the curve at that speed. Now, if I wanted to find the ideal banking angle, all I'd have to do is pretend I don't even need friction. Make the friction parts go away. Now, if I did, there's a friction part. It's got mu in it. I could just drop that out. There's a friction part. I could just drop that out. And my equations would become a lot simpler. So if I assume I'm looking for the ideal banking angle, I don't even need the friction. I'm going to drop the friction entirely. The equations become a little bit simpler. And in order to solve them, I've got n sine theta equals m v squared over r. Here I have n cosine theta minus mg equals 0. If I solve this second equation for n, I'd add mg to both sides to make it be on the other side but positive. I'd divide by the cosine of theta. So then I can take that expression for n, plug that bad boy up there, So now I've got mg over cosine theta times the sine of theta is going to equal mv squared over r. Notice the mass cancels out, which tells me, again, I don't care how heavy my car is as I go around the turn. That's not going to be the determining factor of whether or not I make it through or not. And sine theta over cosine theta is tangent. So I've got g tan theta equals v squared over r. And so there, the velocity that I can take the curve with is going to equal r times g square rooted times the tangent of that banking angle. And you'll notice with the tangent of theta, well, if theta equals 0, the tangent of 0 is 0. But as you make the angle steeper and steeper and steeper, the tangent of theta gets bigger and bigger and bigger. And so what that means is that the steeper I bank that angle, the faster I can go around that turn. That's why they do it on racetracks, because the steeper they make it, the faster the cars can go around that curve before they even need friction to help them at all. And so that's what's happening. And so, had the curve been banked that my sister drove my car through, she probably would have been able to get through in one piece if it had been banked steeply enough. All right, does this make sense? You guys follow along how we're doing this circular motion logic on a non-circular motion sort of problem?
Kind of.
The big thing is to look for that radius of curvature, right? When you see a radius of curvature, you're imagining that even though we're only curving for a tiny amount, that portion of a circle is like the hypothetical extension of a larger full circle. And you can always do the same sort of logic on those that you did there.
Okay.
Whew. So let's keep going a little bit. For this one, I want to talk about the sort of what they call G forces, or the illusionary forces you get when you turn too quickly. If you've ever seen like airplane pilots, like fighter jet pilots, people who fly, at close to the speed of sound and fly their jets, they wear special suits while they're flying. And one of the reasons they do that is because there are some biological issues that you experience while accelerating very rapidly. And what can happen is if you take a turn too quickly, it can cause some issues. And so those suits are designed to help the human body withstand some of those biological stresses that you experience. Now, to understand where those biological stresses come from, imagine that you're a fighter pilot and you're flying in your plane and you take a really sudden turn. So here is my fighter jet. It's got wings. It's got a cockpit. Here's my dude. Here's my dude's feet. So he's inside the plane. Yes, my arc is amazing. And what's going to happen is this guy is traveling at some speed this direction, and he's going super fast. Now, what's going to happen is he's going to turn his plane very, very rapidly. In some portion of a circle. Now, here's the issue. If he turns his plane around, there's going to be some circle where his head is going to travel in a circle. His feet, however, are going to be traveling in a smaller circle because they're closer to the center of the circle than his head is. So what that means is that different parts of his body are going to travel around different size circles. He's going to experience a different acceleration at each of those locations. Well, what would the difference be? Well, in order to do that, I need to figure out how is the velocity different from his head to his feet. Well, making this turn is going to happen in a certain amount of time. right? The time it takes for his head to whip around to here is the same as the time it takes for his feet to whip around to here. So the time for those two things is the same. However, his head travels around this size arc, so it's going to travel a much bigger distance, whereas his feet are going to travel around this size arc, which is a smaller distance. So if I'm thinking in terms of velocity, and velocity is change in position over time, what's going to happen is his head is going to have a big change in position, but in the same time that his feet has a small change in position. His head and his feet will be traveling at different velocities. And of course, if his head and his feet travel at different velocities, that means that his head and his feet will experience a different acceleration because the v will be different. So what's kind of cramping our style here is that we're trying to describe the motion of this plane in terms of a velocity, but different portions of the plane or different portions of the pilot, all of them are going to end up having different values of velocity. So sometimes it's helpful when talking about things that are turning or spinning or rotating to talk about them in language that is better able to capture what's happening there. And that's where the concept of angular velocity is going to get born. And what angular velocity is going to do is it's going to allow me to capture the motion of this object in a way that's the same. In other words, I can talk about the angular velocity of the dude while he rotates. And I won't have to specify whether I'm talking about his feet or his head because they're both going to have the same angular velocity. Now, in order to do that, what I will do is I will say the angular velocity, for which we'll use the Greek letter omega, which kind of looks like a scripty W, but it's not a W, it's the Greek letter omega. So I die inside a little bit every time you call it a W. But we're going to define that as the angle that you rotate through divided by the time through which you rotate through that angle. And notice if we couch things in those terms, well, this dude's head is going to rotate around 180 degrees or pi radians. This dude's feet are going to rotate around 180 degrees or pi radians. So his angular velocity is going to be the same for his head as it is for his feet. So when I'm talking about the rotation or the rotational motion of this plane, the rotational motion of the plane is going to be the same in terms of angular velocity for every portion of the plane. I can describe its motion with one number rather than specifying different numbers for different portions of the object. That's super, super helpful. And what's going to happen is if I look at things this way, there should be a relationship between what angle I rotate through and how far I've gone. Those two things ought to be connected. And to see what that connection is, it's super easy. Because imagine I have an object that goes around in a full circle. Right? If I go all the way around one full circle, what angle have I rotated through? Well, one full revolution would be 360 degrees. And we're going to find that it's going to be more natural to use radians. And I have to remember that 360 degrees is 2 pi radians. So if I go 360 degrees, I've gone 2 pi radians. How far have I traveled? How many meters is that? Well, the distance around that circle, the delta x, if you will, would be 2 pi times r, right? That's the circumference formula. And when I do that, I notice something, right? Oh, look, the distance around the delta x, or we'll use the term arc length all the way around was 2 pi times r. But what's the 2 pi? That's how many radians I went. This is how many radians I spun around times the radius of the circle. Boom. If I go halfway around, that's 180 degrees or pi radians. But how far would that be? Half of that, pi r. So it turns out the arc length, the distance around any arc, is just going to be the change in angle, the delta theta, times the radius. And that's going to be generally true. But wait a second. If that means that my velocity is how far I went, so delta theta times r over delta t, I'm just replacing the delta x with this. Well, look at that. Delta theta over delta t is omega. That means that there's a relationship between my linear velocity in meters per second and my angular velocity in radians per second. So if I know v, I can find omega. And whereas omega is going to be the same for every part of the person, the linear velocity is going to be whatever that omega is times the r. So I'm going to have a bigger velocity for his head because the r is bigger for his head, and a smaller velocity for his feet because the r is smaller for his feet. Neat. So now, if I'm using that, if I'm thinking about the centripetal acceleration as being v squared over r, but I know that v is equal to omega times r, I could rewrite my expression for the centripetal acceleration, and I could say that AC is going to equal this squared over r. Notice this and this cancel. So I can say that AC is omega squared times r. So what's going to occur is, you'll notice my centripetal acceleration is going to be my angular acceleration, which is the same for every portion of my jet pilot, times r, which is going to be different for his feet than it is for his head. So if I'm dealing with my jet pilot zipping around in a circle as he whips around, well, what are the forces acting on him? Well, he's going to have the plane pushing him towards the center, some sort of normal force from the plane, and that's it. And that'll be ma, but a is equal to omega squared r. And so what that tells me is that the force that he's going to have exerted on different parts of his body is going to get larger with r. So near the outside of the plane, he's going to have to get pushed super, super hard to hold that curve. Near the center of the plane, or near his feet, he's going to get pushed not quite as hard. And remember how we always perceive the force of gravity based on the size of the normal force acting on us? Well, this tells me that for this guy, it's going to seem like the force of gravity at his feet is different from the force of gravity at his head. It's going to feel very different at his feet than at his head. And that has important biological impacts on you. Because imagine like what happens in your body when you're standing up regularly. You've got a force of gravity pulling all the blood in your body toward your feet. And what happens is, in order for you to pump the blood from your feet back up to your heart, you've got to push. You've got to have pressure in your legs pushing the blood upward against the force of gravity so that it can circulate through your body and get reoxygenated. And your body can handle this just fine. We've evolved to do that. But now imagine you're not just standing around. Instead, you imagine you're that fighter pilot and you've made a turn so that the effective force of gravity at your feet is, say, larger than the force of gravity at your head. That means the blood is being pulled down towards your feet, and your body has to work a little extra hard to push the blood out of your feet and back up to your heart so you can reoxygenate. Now, if you make that curve too quickly and your feet are toward the outside part of that curve, what's going to happen is blood will end up pooling up in your feet, which means it's not getting back up to your heart, which means it's not getting reoxygenated. And the next thing you know, the oxygen levels at your brain start to drop. And if you're that fighter pilot and you've made that turn too quickly, what's going to happen is the lack of oxygen to your brain is going to make you start to first get dizzy. Eventually, it may cause you to pass out. right? They call it blacking out. And that's not a thing you want someone to do when they're flying a, $15 million plane, right? You would like them to stay conscious because they cannot keep you in the air if they are sleeping. So if they turn too quickly, that's a problem. Now, what those flight suits do that they wear is they're pressurized. They literally have little air bladders in the feet area to squeeze a little bit on their legs. And that causes extra pressure that pushes the blood out of their feet a little bit more effectively, so that when they take those high velocity turns, the blood doesn't pool in their legs as much, because their heart can't push the blood out of their feet. The leggings they're wearing help push a little extra hard to keep that blood flowing to their brains, so they can stay conscious during that high velocity maneuver. And the same thing would happen if they were to turn and have their head towards the outside part of the turn and their feet towards the inside part of the turn, the way that I drew it here. Here, their feet are going to have a smaller radius than their head. So here you'd have the opposite problem, right? The blood in their bodies would be pooling up in their head rather than at their feet. But either way, you'd have the same issue. Your heart would have to work extra hard to push the blood from your head back down to your heart. And so someone who has that condition is going to have the exact same problem. However, because of the pooling of blood in your head, they tend to sort of see like a little bit pink, because all the blood pooling in their eyes before they pass out. So pilots often refer to that as redding out rather than blacking out. But it's the same effect. Their oxygen levels are dropping and they lose consciousness. And so they have to be able to utilize that sort of effect either way. So that's why these high velocity or high acceleration turns can be so problematic. A few years ago, there was an article about an artist who had devised a method of execution. And his method of execution was a roller coaster. And the shape of the roller coaster was like this really huge first hill. And then what you had was a series of smaller loops. And what's going to happen is, the reason this was an execution method is because this hill was so high that when they got down to the bottom, they were traveling so fast that as they're going through all of these loops, the centripetal acceleration ended up being somewhere in the excess of about 10 times the acceleration of gravity, or about 98 meters per second squared, sustained for the rest of the ride. And that's going to have the exact same experience. Your head is going to feel a slightly smaller acceleration in the middle of that loop as you take that roller coaster than your feet would at the outside. So the blood would pool in your feet, and the entire time the ride is going, you wouldn't be getting enough oxygen to your brain. And so you'd be having a really cool method of execution. You'd have a lot of fun on this roller coaster up until you passed out and died. But the idea was that you would be euphoric and painless and pretty crazy. No one's ever going to build this thing. That's horrifying. But that's the sort of physics behind the idea. Super cool. All right. Any questions about that part of circular motion? All right. I'm going to let you guys go out a little bit early today because we're a little bit ahead of schedule. We're basically done with chapter 6. We'll probably take some questions about it tomorrow. So if you've got some homework questions, you should definitely field them tomorrow. But then it's going to be onward to chapter 7. Exam 2 is going to happen early next week, and it's going to cover chapters 4, 5, and 6. So if you haven't started cracking at those homeworks, make sure you do it soon because time's a-wasting. All right. I'll see you guys later. Have a good day.
I'll be in your office hours.
I figured. Yeah.
Okay. Thank you.
Bye.